Let's take a look at an example problem here where we're going to look at determining the speed of sound, the velocity at which a sound wave travels through an aluminum bar. And to do this, we're going to use some terms that we've used before, we've learned before. First is Young's modulus. Young's modulus for aluminum is 7 times 10 to the 10th Pascal. And the density, or rho, for aluminum is 2.7 times 10 to the third meters or kilograms per meter cubed. So the stem of the problem says if a solid bar of aluminum is struck at one end with a hammer, a longitudinal pulse propagates down the bar. Find the speed of sound in a bar of aluminum. So what we need to do is set this up with the relationships with Young's modulus and density. To find the velocity of sound, the speed of sound, in this aluminum bar, the relationship is the square root of Young's modulus divided by the density. Well, we've got our terms here for Young's modulus, 7 times 10 to the 10th Pascal. We've got our density, 2.7 times 10 to the third kilograms per meter cubed. This is all good, except we don't have common terms. I mean, we're going to, in the end, we'll come up with a value, but how do we know that it's meters per second? How do we know that it was actually has the right units? So what we need to do is move to the next step here is we know that a Pascal is a Newton per meter squared. Well, that gets us closer. So now we have newtons per meter squared divided by kilograms per meter cubed. We need to break it down more. We need to tease out the fundamental units out of this Newton. Well, if you remember, the fundamental units of Newton is a kilogram meter per second squared. So now, if we substitute for newtons per meter squared, kilogram meters per second squared, keep the meters squared, the rho in the denominator has everything we need. So now we're set up so that terms are going to start canceling. So our kilograms are going to cancel. We're going to end up with meters and meters squared and meters cubed are going to cancel, so that what we have left over is meters per second squared. So now if we move to the next step, we have 7 times 10 to the 10th meters squared per second squared, okay? Because all of those other terms teased out, and it simplified and left us with our second squared here, and this will have another unit of meters added. So 2.7 times 10 to the third into 7 times 10 to the 10th gives us 5,100 meters per second when we take the square root of the value. If we do one more step, if we do our conversion from meters into miles, meters per second, then miles per hour, we end up with about 11,000 miles per hour is how quickly that longitudinal pulse propagates through that aluminum bar. But again, we had to make sure that we had all of our units correct. So again, I hope you're relying on the information you're keeping in your notebook so that you can go back quickly and determine if you have the right units available to solve for these problems.